Hey, what's up guys? It's been a long time since I made my last video, and now I thought to myself, okay, it's finally time to cut to the chase and get back to making maths videos, and this time I thought about making it as a series. So we're gonna go through this right together. Anyway, this video, as you read, is about eigenvalues, or as some of you American folks, or maybe as European, like to call it eigenvalues. So let's start with this particular example I decided to work with, which involves fractions. And so we have so the aim is to calculate the eigenvalues of this matrix A, where we could use this particular method, which is, in other words, the determinant between a matrix A minus lambda, where lambda is going to be the eigenvalues to whatever polynomial order, in this case 2, times the identity matrix I, where we define I, which looks quite horrible underneath, as 1 across the diagonal with 0 everywhere else. Because it's a 2 by 2, it's quite straightforward. Okay, so let's solve this thing. So first things first. Okay, so first we want to take a minus lambda I. So lambda I, we stick a lambda here, so we multiply the matrix by lambda. In other words, over here we could just say lambda I equals, for every single case, lambda here 0, 0, and lambda. So 1 times lambda, 0 times lambda, and so on. Now, what we want to do is calculate the determinant between the matrix A minus this matrix. So we could just start pretty straightforward. So what we have is A minus lambda I, and this equals, so half take away lambda is half minus lambda, minus 3 over 2, take away 0 is minus 3 over 2, minus 3 over 2 take away here once again, minus 3 over 2, and then lastly half, subtract this, is once again half minus lambda. So now we just take the determinant of this and equal it to 0. Let me change my pen because this pen is very ugly. I'm gonna start using red. Okay, so to calculate the determinant, the way it works is that we multiply the diagonals across and subtract it against the diagonals on the other side. If it was an n by n matrix, we have a series of diagonals. Thankfully, under 2 by 2, we just multiply these two, subtract these two. So, what do we have? Minus half minus lambda times half minus lambda, we can just write it as half minus lambda squared. Now we're going to subtract the multiplication of these two terms. Minus 3 over 2 times minus 3 over 2 is 9 over 4. So we're going to subtract 9 over 4 and equal to 0. So using what we learned back in high school, quadratic techniques, we can plus this across and then take the square root. So I'm just going to do it in one go. I'm just going to assume you guys already know how to do this. Okay, so it'll be 9 over 4 on the side, take the square root, it'll be plus minus square root of 9 over 4, square root of 9 is 3, square root of 4 is 2, so plus minus 3 over 2. Alright, so here we are, already at the end of the video. So an eigenvalues, remember, is the value of the lambda. Our lambda in this case, we're going to have two values, a plus and a negative. So solving this directly, we can see by plus and lambda and subtracting this, we're going to get lambda equals half plus minus, I can't be able to write minus plus, I don't like the way it looks, 3 over 2. And hence, we're going to get two solutions where we're going to say one is lambda 1 and one is lambda 2. And the values for these eigenvalues, so remember these are the eigenvalues which we just calculated, are, so half plus 3 over 2 is 4 over 2, which is 2. And then half take away minus 3 over 2. If you can't do it mentally, the calculator will suggest is minus 1. And that's it, guys. This is how you calculate the eigenvalues. And well, the next video will probably be close to eigenvectors and how we incorporated techniques here. But anyways, this is pretty much the gist of it. Hope you guys understood this example. It's very clear. So just a quick recap. You take the determinant of this matrix A minus lambda times identity matrix, which gives you a form of this where I is this matrix. And hence, just using some basic mathematical and algebra techniques, we conclude that lambda, the eigenvalue, has two eigenvalues. One is 2 and minus 1. Done. Thank you for watching, guys. Hope to see you again.